Section 310, it's time for some logarithmic regression. So we're going to compare the average rate of change in an increasing logarithmic, a linear, and an exponential function. We're going to do some regression equations of the form y equals a plus b times the natural log of x to best fit a data set. So in our first question, we're back at that pedestrian data that we saw at the beginning of section 3.9, where it's talking about the average walking speed. And we observed in that section that it was not linear, it was not exponential, but does it possibly appear to be logarithmic? We can say, now that we know what a logarithmic function looks like, we can say, yeah, it kind of fits that pattern. It's a logarithmic function, and it is increasing more slowly over time. Okay, so I'm going to fill in the table from the dots up here. Initially, we have the 50, and then 3.7, then 100, 4.3, 200, 4.9, 500, 5.7, 1,000, 6.3, and 2,000, 6.9. Okay, so I have to go ahead and enter this data in Desmos. Let me get my Desmos window pulled over. Making a table. And we're going to start with, 50, and then 100, and then 2, I didn't hit enter, goodness. 200, 500, 1,000, and 2,000. All right, and then I'll zoom over on the data. Oh, I messed something up. Oh, there we go. Lovely when you can figure out what you messed up. There we go. I had my 100 typed in incorrectly. That looks a lot better, and that should match what's going on with the data set. Okay. So now we're going to do the regression. So I need to know what the equation looks like. As we see in the book, it looks like y equals a plus b natural log of x. And so I'm going to make my usual regression changes, x1, y1, tilde, and so on. So I'm going to type in y1 approximately a plus b natural log of x1. Ta-da! So we'll note to ourselves for regression, what we will type is y1 approximately a plus b natural log of x1. Okay. Now, when we talked about exponential functions, we talked about the log mode box. And I see the log mode box here again. So let me copy and paste this real quick and compare those two when I check and uncheck the box. All right. So unchecked, my A parameter is 0.3033. Checked, 0.3033. Okay. B value, 0.86801. Oh, they're the exact same. Okay. Reason for this is that the log mode box uses the logarithm of some values to compute to simplify the process. But it's a logarithmic model, so I'm already using the logarithm of the values. So there's no difference in checking or not checking. It doesn't matter. So whatever you want. It's not going to have any difference on your parameters. So we have to check them for the exponentials. If you want to check it, just go ahead. I'm just going to leave it for now. But because they're the same, just trying to make sure we understand that I don't have to check them because I'm not getting a difference in the parameters in the logarithmic model like I do for the exponential models. Okay. They would like us to record our function down here. So I'm going to write it down with our parameters. So y equals, the a parameter is 0.303. They said round to the nearest thousandth, which means 3 places, plus 0.868 natural log of x. Again, I don't know why I write mine in cursive, natural log of x. I don't know why. It's just to tighten my function together. Sometimes I remember to not, like I remember to print sometimes and I forget to print other times. So Don't mind if I write my natural log in cursive versus write the ln in print form. Same function, natural log of x. Okay. Enter the function in the calculator graph. Oh, okay, well, that happens naturally. It's a good thing we don't have those old-fashioned calculators. It happens automatically on decimals. So verify it's a good fit. Yep, looks good. Those dots are really close, and I can also see that my r-squared value is 1. Does that mean it's perfect? No, it does not mean it's perfect. If I zoom in on these dots, I'll probably see that they're not right on the line. It's not perfect. It's just it rounds to 4 places, so there were 0.9999 something else, so it rounded it to 1, but it's really, really darn close to 1. Okay, so it's a good fit. What is the practical domain? Okay, so this is population of a city in thousands. We can plug in, 50,000 was our lowest city. I can't get down to 0 itself, because first of all, I know that 0 can't go into the logarithmic function. And it wouldn't be a city if there was no people in it. So a small city would have a couple thousand. Towns, I don't know. So maybe we'll go with 1,000. Maybe we wouldn't even call it a city at 1,000 people, but we might go. I'm going to include if I use like 1 or something. 1,000 for my lowest, just to say, that's a pretty small city. Village, town, whatever you want to call it. Okay. And then up to, so we already had a city that was 2,000, and that's 2,000 people, which means 2 million people. I can go bigger than that. I can go up to 5,000, which would be 5 million people. I can probably go a little further than that. Let's go for, let's see, New York. They've got 8 million people in New York City. So let me just go to like 10 million. So I'm going to use 10,000. Now, I'll have you note that I went quite a long ways on this one. When we had exponential functions, our exponential functions broke down very rapidly because they grew so fast. Our logarithmic functions are going to have the opposite problem. They're going to grow very, very slow. And so I can go a bit further and get predictions that aren't going to be terribly high compared to the current prediction. So I'm not worried about going far past the edge of the data. It's going to break down eventually, but I can go a little bit further than I might have went in some of the other types of modeling because the model's not going to grow very rapidly. So I went a little ways and said 10,000 just to stick us somewhere above New York there for this model. Okay. It also would have been okay to have done parentheses 0 up to say 10,000. Just as another option, to say that 0 was my lower limit. I did not want to have 0, but maybe I could add 50 people in a city. I don't want to call it city, but that bracket around the 1 as my lower limit. It's a little bit flexible. Okay, so use my function to predict the walking speed when the walking speed will be, no, what the walking speed will be for a population of 589,121. So the units are in thousands. So I'm going to want to plug 589.121 into my function. Okay, let me just write in function notation because that's how I like to do this. So f of x equals my a number, 0.303, plus my b number, 0.868 times the natural log of x. Then I can do f of 589.121. All right. So f of 589.121 gives us 5.84. I need some units real quick. Feet per second for the walking speed. All right. So within reason, it looks like our last data point had 2 million people in the city, and they walked at 6.9 feet per second. So that's just somewhere in the middle for our prediction. All right, so now I want to use my model to predict the average walking speed in New York City with population 8 million. And so this time I'm going to want to do f of 8,008.278 to again convert that 8 million into 8,000, 8,000. So f of 8,008.278 will give us, oops, I forgot the f. There we go. Will give us a prediction of 8.1 feet per second. And again, that's pretty fast. I don't know if that's accurate or not based on the actual speed in New York, but it's faster than our ending prediction. So it's in the extrapolation range. We got a little more margin for error on this prediction than we have for the first one. So rapid pace. Okay. Now, so again, it's just less reliable than the first one. That's just all I'm trying to say there. Okay. So for the next one, if the average walking speed is 5.2 feet per second, write the equation that can be used to determine the population. Okay, so this is going to be our output. And so we would have 5.2 as an output being equal to the 0.303 plus the 0.868 natural log of x. That would be the equation used to solve it. Now, if I solve it using the graphical approach, we're going to be graphing y equals 5.2, and we're going to be intersecting it with our function. So let's do that. So the intersection point is at 281.9, comma 5.2. So this means that a city with a population of 281.9 thousand would have a walking speed of 5.2 feet per second. Okay. So I'm going to fill in a table for the same function. So note that this is the function I used before. They changed the names on me, so I guess I can change mine to match. They called S of, and they want this called P. Same function though. So now I want to evaluate, I'll just do this in a table. They want me to evaluate the function S at a new set of inputs, 10, 20, 150, and 250. Okay, so I've got 2.30, 2.90, 4.65, and 5.1. If I round those all to two places, that's what I would have. Okay, so determine the average rate of change as the population increases from 10,000 to 20,000. So when they ask me about average rate of change, this is regular slope. So that's just the regular slope here. So we're going to compute 2.9 minus 2.3 over 20 minus 10, just the regular average rate of change like we would have done in chapter 1. And we're going to compare these average rates of change and see how they are changing. 2.9 minus 2.3 over 20 minus 10. So 0.6 feet per second per 1,000 people. So between 10 and 20, the average rate of change means that the speed, walking speed, increases by 0.6 feet per second per 1,000 people. Now that's going to change if I look at it between another set of ordered pairs. Okay, so now we're going to compute it again between 20,000 to 150,000. So at 150,000, there were 4.65 as the walking speed, and 20,000 it was the 2.9 over 150 minus 20. So we have 0.013, and again before it was, from the previous one, it was 0.06. Now we're at 0.013. And we get to do it again for the 150 to 250,000. So this one's going to have the 5.1 minus the 4.65 over 250 minus 150. And I have 0.005. So what we're supposed to be observing between these values is that if this was linear, the rates of change would be the same. If this was exponential, the rates of change would be increasing. Since it is logarithmic, the rates of change are decreasing. So the rates of change are decreasing. Let's just say that. All right. So another way to say that, as they have done so, is that as the input of the logarithmic function increases, the output increases, but at a slower rate. So it's still increasing, it's just increasing at a decreasing rate. So it's increasing at a decreasing rate, at a slower rate. Okay, so for an increasing linear function, as the input changes, the output, as the input variable increases, the output variable increases at a constant rate. For an increasing exponential function, as the input increases, the output increases at an increasing rate. And for an, again, I guess I should underline increasing function, because obviously our functions could decrease, but in this example, for an increasing linear function, increasing exponential or increasing logarithmic function, the output is still going to be increasing, but at a decreasing rate. Consider the graphs of these three functions. We looked at these graphs in the last section about inverses, looking at e to the x. I guess I can name them as they've done with f of x instead of y. Okay, which of the functions are increasing? All of them. They're all, as you trace left to right, getting larger, getting larger, getting larger. The exponential gets in faster at a faster rate. The linear function gets faster at a constant rate, and the logarithmic function gets faster at a slower rate. So which functions are increasing? All. Which functions are decreasing? None. As the input values get larger, which function grows fastest? The exponential, which is our f of x equals e to the x. As the input values get larger, which function grows more slowly? The logarithmic. That's our g of x equals natural log of x. Okay, next page. Do any of these functions have a horizontal asymptote? Yes, the exponential does. The exponential function has a horizontal asymptote right here on the left side of it. Do any of these functions have a vertical asymptote? Yes, the logarithmic function on its, again, its left side. I mean to say, the left side of this function. So the logarithmic. Compare the domains of these functions. Okay, so I'm going to write the linear function first, and then I'm going to look at the exponential function, and then the logarithmic function. And I'm just going to header them up here, and we'll talk about their domains and their ranges for those titles. Okay, so for the linear function, its domain, you can plug anything into it. So negative infinity to infinity. And then its range is the same thing. You've got the linear function spanning into the positives and negatives both on x and on y. Then for the exponential function, the domain, it's going left to right. It's going to have anything in it. So the domain is going to be negative infinity to infinity. But the range, this thing never goes below the x-axis here. It never goes down into the negatives in output. So this is going to have only positive outputs. For the logarithmic, the domain of the logarithmic is I do not get to have any negative x's, so I have only the 0 and up for the inputs. But for outputs, I certainly go down into the negative outputs and up into the positive outputs. So we have negative infinity to infinity there. Just wanted to put these two functions next to each other, the exponential and logarithm, to re-emphasize the fact that they're inverses, and so their domain and their ranges flip-flop. Linear is out by itself. It's not having anything to do with the two. It's just as a comparative piece because it's the other type of function that we have studied so far. All right. Okay, so we are dropping a ball and watching it hit the ground, and the bounce, the amount that it bounces back, is decreasing over time. And so the height is decreasing over time. Looks like that's going to be a logarithmic function. And we have a table, and we want to graph this table. So that's the first thing we'll do is get this table entered. Now we're just going to graph the top and the very bottom, the total distance. So I don't need that middle one. The middle one's just to help us compute. So I'm going to do 1, 2, 3, 4, 5, 6, and the 20, 30, 35. Just missed a 3 there. And the last one. So once all of those have been graphed, we can see that it does increase at a decreasing rate. So it should be a logarithmic model. Let's go over to our next page. Do the table and scatter plot indicate that the data is linear, exponential, or logarithmic? Well, it's going to indicate that it's logarithmic because it's increasing at a decreasing rate. Because the shape is like this, and it increases, but at slower and slower pace. Increases at a decreasing rate. So again, you have a picture in your mind that linear, straight, exponential, increases at an increasing rate, and logarithmic increases at a decreasing rate. Produce each regression. Okay. So the linear, y1 approximately mx1 plus b, not too good. Exponential, y1 approximately ab to the x1, not too good. Even if I turn on log mode, even worse. And logarithmic, y1 approximately a plus b natural log of x1. Oh, okay, so let's turn those two off. Better. It fits the data better. Again, no model would have been perfect for this data set, but I do get to see that I'm increasing at a decreasing rate here. And again, checking my box doesn't do anything. Gives me an additional R value, but doesn't do anything to my parameters. Okay. So they want us to write them all down. Okay, so the equations here, if I slide this back over, I can see them. So our linear equation would have been y equals 3.59 x plus 20.88. The exponential would have been y equals 21.37 times 11.002 to the x, and the logarithmic is, oh goodness, I just messed those two up. I scrolled down further than I thought. So this one was 21.37 plus 11.002 natural log of x. I just scrolled down too far. I didn't realize. I was trying to scroll down to this one. Or maybe I got confused because those numbers are pretty similar. I don't know. I somehow messed up the exponential. So it does start with 21.37, it looks like, and then it's 1.128. Should have thought about that 11. I was like, that's way too big for it to be a base, but I wasn't really thinking about it. So there we go. That one was the exponential, and this one is the logarithmic. Graph each, which is best. It's logarithmic. No surprise. Now use the equation of best fit to predict the total distance the ball travels when it hits the ground for the 10th time. So we'll rename this thing as f of x. And we want f of 10. .7. I believe our units were feet. So between all its bounces, after it bounced 10 times, up, down, up, down, up, down, up, and then its smaller bounces included, it would have traveled a vertical distance of 46.7